Alright, so I want to talk about the toilet paper roll problem where you hold the toilet paper here and let it fall, and we want to find the linear acceleration. And one of the reasons I decided to do this video right now is because after kind of talking about this in class, I thought about the problem a lot over the last couple of days, and I realized that this is a great opportunity to highlight some potential sources of confusion and some of the different ways we can analyze a single situation. And just to be perfectly honest, I was really confused about it at first, and then I realized I was making some mistakes too in my analysis. So the first way I want to look at it is this. Let's say that it's rotating around this point. Okay? If it's rotating at this point, we can look at two things. There's two forces acting on this roll. We have the upward force of tension and the downward force of gravity. Tension pulling up on it from this perspective is going to cause no torque, okay, because the radius, if we're saying it's rotating about this axis, the radius of that rotation is 0, okay, and so no torque comes from tension, but we do have torque from gravity, okay. In addition, we can talk about the net force here. We have, well, actually, we don't even need to worry about that here in this particular case because of the fact that tension does not contribute to the torque. Okay, so we're going to write a net torque equation. I alpha is equal to the sum of the torques. Let's say that this way is positive, which means that mg is also going to cause a positive torque. So this will be mg times r. The moment of inertia for the toilet paper roll is going to be moment of inertia for a tube plus mh squared. We're using this because this is the center of mass and it's rotating at this point. So I for a tube is going to be 1/2 times m times little r squared plus big R squared. And here it's going to be m times big R squared for that outer radius. Okay, and so we can simplify this before we plug it in. I'm going to distribute the 1/2 to each of these, so it's, and we'll factor m out from everything, so it's m times 1/2 r squared plus 1/2 big R squared plus big R squared. Okay, and this gives us m times 1/2 r squared plus 3/2 r squared. Okay, and then maybe to simplify things, we'll factor the 1/2 out. So 1/2 m r squared plus 3 big R squared. That will be our moment of inertia. We'll take that and put it here. Okay, in addition, let's say that, let's go ahead and replace alpha with a, since we want to solve for a. Now, there's the important piece here that I've been ignoring in class, and I never really thought about this way until I just kind of realized why this is really important. So we can say that up or down is positive, and it's going to be completely arbitrary. Let's say, though, for the sake of this problem, that up is positive, because I'm going to keep it consistent for the 3 ways I'm showing it, which means down is negative. Okay? So when we write our equation that A is equal to alpha times R, we have to think about something. When we have angular acceleration this way, okay, as it accelerates this way, that means it's accelerating downward. This is a positive angular acceleration, but as it goes downward, that's a negative linear acceleration, which means that this is negative, okay, because these are going to be opposite signs in this case. When it's accelerating this way, and that means it's accelerating downward at the same time. So these are, when we have a positive angular acceleration, that means a negative linear acceleration for this circumstance. Okay, and so that's why I'm putting the negative there, which means that negative a over r is equal to alpha. So I'll put that in. So I'll put both of these sets in. So we have 1/2 big M times r squared plus 3 times big R squared times negative a over r equals mg r. Okay, the m's cancel out. We're going to divide r over. Okay, so 1/2 r squared plus 3 r squared. We'll put the negative in front. Then times a over r squared equals g. So multiply across the divided by big R squared, we'll divide that to both those. And let's multiply -2 to the other side, okay, to get rid of this negative 1/2. So r squared over big R squared plus 3 times a equals -2g. I'll divide this over and get that a is equal to -2g over little r squared, big R squared, plus 3. Okay, so that is our acceleration, and hopefully we'll get that using the other two methods. For the next method, what we're going to do is say that the point of rotation, instead of setting it here on the edge, we're going to say it's here in the middle, okay, where the center of mass is. Okay, so if we say that the point of rotation is here in the center, then this right here is a torque from tension. We have the downward force of gravity. This does not cause any torque. Okay, and so we're going to say, all right, well, I alpha is equal to, we're going to say that that's a positive torque here. Okay, so positive T times R, because we're going to say that this way is positive. And then we're going to say, okay, so moment of inertia. This time we don't need the parallel axis theorem because it's rotating about its center of mass. So we're going to say 1/2 m little r squared plus big R squared. Okay. For alpha, so a equals alpha times r. When we have a positive angular acceleration, that means it's going to be spinning down like this. That is going to be the equivalent of a negative linear acceleration. So alpha is equal to negative a over r. Okay, so we'll plug both those in. So 1/2 big M times little r squared plus big R squared equals, times negative a over r equals T times R. Okay, now we're going to look at the forces here. We have the upward force of tension and the downward force of gravity. We didn't have to do this last time. The reason we have to do it this time is because we have this force of tension that we need to get rid of because we don't know what it is. Okay, so we can say MA equals, again, we're saying that up is positive because acceleration is going to be negative. Okay, MA equals T minus mg, or T equals MA plus mg. We'll go a step further to say that T is equal to M times A plus G. Okay, so we're going to put that in here for T. So we have 1/2, and I'll distribute the 1/2 over. So we have M 1/2 little r squared plus big R 1/2 big R squared. We put the negative in the front. A over R. Let's divide the R over 2. So A over R squared equals, and then T is equal to M times A plus G. Okay, so we can, and this, that's a little, okay, so we can cancel out the M, so we get negative 1/2 R squared plus, leave it in the front, plus 1/2 big R squared times A over R squared equals A plus G. Okay, so we're going to subtract this A over, and we'll divide the R squareds over 2, so we get negative, parentheses, 1/2 R squared over big R squared plus 1/2 times A minus A equals G. Okay, so I'm going to divide this whole side by -1. So this becomes negative. And I'm going to factor out A at the same time. So we have parentheses 1/2 R squared over big R squared plus 1/2 plus 1 all times A equals -G. Okay, 1/2 plus 1 is going to be 3/2. Let's factor out 1/2, or let's actually just multiply everything by 2. So we get R squared over R squared plus 3 times A equals -2G. And finally we'll divide this over and get A equals -2G over little r squared over big R squared plus 3. Okay, and so this is the same answer that we got from the previous one. Okay, so we've gotten the same answer 2 different ways. Okay, -2G over little r squared plus big R squared plus 3. Okay, and we're going to do this one more way now. We can also do this thinking about energy. Okay, the fact that we start with potential energy in the roll of toilet paper, and as it falls, that potential energy is transformed to kinetic energy. The trick is, though, that it's going to convert to both linear kinetic energy and rotational kinetic energy. Okay, so we're going to do this from an energy perspective.